Okay, so in this video we'll be going over the divergence theorem. So here's a statement, let me read it. It says let S be a closed piecewise smooth surface which is the boundary of the solid Q. If S is oriented by the unit normal vector directed outward from Q and F is a vector field whose component functions have continuous first partial derivatives in Q, then the surface integral of F over S equals the volume integral of the divergence over Q. Or another way of saying this is the flux of F through S. So it's fairly complicated here. We're going to look at a proof of a special case of this in a second. Let me just remind you what the divergence is. Let me write it here. Okay, so recall that the divergence, another way of writing it would be the del operator dotted with F, or divf. So divergence is defined to be the first component function of your vector field derivative with respect to x plus second component function derivative with respect to y plus third component function derivative with respect to z. So this is our divergence. Okay, so now let's take a look at a special case of the divergence theorem. Okay, so let me make a definition first. So let me erase a few things here and we'll keep going. Okay, so let P0 be some point in 3 space. Let delta x be some number, some positive number. Let delta y just be some positive number. And delta z be some positive number. So we're going to make a definition now. So here's the definition. Okay, so we're letting R of subscript P of 0 of delta x, delta y, delta z denote the rectangular box I have here. So in the vertice down here is my P0 point, x0, y0, z0. I'm assuming, the way I'm drawing it here, I'm going to assume the x-axis is along here, parallel to this, and the y-axis is parallel to the one back here, and the z-axis is parallel to the one here. So here's my point x0, y0, z0. So if I travel along here, delta x would put me at x0 plus delta x, comma y0, z0. Then I can travel from here to here. This would be along the parallel to the y-axis. So therefore, traveling along here, I travel along delta y. So it'd be x0 plus delta x, comma y0 plus delta y. Should be comma here, comma z0. Then I can travel from here back, but I would put me back at x0 then, and then it'd be y plus delta y z0. Then here I can travel up from here, delta z, so it'd be the same point except at z0 you'd have a plus delta z, which I have here. Then I can move back and so forth. That's how I'm getting all these vertices. And this vertice here that I haven't marked would be x0 plus delta x, y0, comma z0 plus delta z. So let me put that here. Okay, so the point would be x0 plus, whoops, it should be delta x here. Because you're going here and then you're going, keeping the same y, but you're moving up delta z on the z-axis. That'd be the point here. That's how I name these. Now I'm going to label the faces of this. So let me make some assignments here for the faces. Okay, so I'm going to let S1 of xy equal a top face up here. So I want to parameterize now the top face. Notice here in the top face, the z value on the top face is constant and it's z0 plus delta z. And the x can be anything from that x value, which is x0, to x0 plus delta x. And the y can be anything from y0 to y0 plus delta y. So we write it here and I'll explain. So parameterizing the top face would be then I claim x comma y comma z0 plus delta z, where the x goes between x0 and x0 plus delta x, and the y goes between y0 and y0 plus delta y. Again, because you're on a top face, since you're on a top face, the z value is fixed at z0 plus delta z, and the x can range from x0 there all the way to x0 plus delta x here, and the y can range from y0 here all the way to y0 plus delta y. I'll pick up all the points in here. Okay, so that's how you parameterize the top face. Let's do the bottom face next. Okay, so let S2 of xy be the bottom face, which I have here, so bottom down here. So note on the bottom face, the z is constant at z0 on the bottom. And the x can range from x0 to x0 plus delta x, and the y can range from y0 to y0 plus delta y. So we parameterize the bottom face as xy z0, where the x and the y have the same range as the top face. Okay, let's do now the right face. So this guy will be here. So let's do that one next. Okay, so the right face, let's call it S3. So it's going to be then, it should be actually a z here, not a y. Okay, so it'd be z here. So it should be a function of x and z. Because the right face is over here. On the right face, notice that what's constant is the y0 plus delta y. That's constant on the right face. So it means the x and z can vary between, so z can vary between z0 and z0 plus delta z, and x can vary between x0 and x0 plus delta x. So that's my right face parameterized. Let's do, say, the left face next over here. Okay, so now my left face I'm calling S4. It's going to be a function of x and z. That's here. So on this left face, the y is constant. It's y0 on the left face. So the x and z will vary. So this will be how you parameterize the left face. And now let's do the last two faces. Okay, so let's keep going. Okay, let's call S5. It's going to be a function of y and z. The front face. So the front face here. So notice on the front face, these four vertices here, they all have the x0 plus delta x. So that's constant in all those. And the y and z can vary. So like this. And lastly, let's do the back face. Okay, and lastly on the back face, let's call it S6. So it's going to be a function of y and z. So back here, the x is constant x0. It's going to be x0, then y and z can vary. That's how you parameterize the back face. Okay, so we've parameterized all the faces now. Let me erase some things and we'll keep going here. I'll erase some things and summarize what we have and keep going. Okay, so summarizing, we have our top face parameterized here. I'm claiming the outward normal vector from our rectangle is q on the front face, top face. So let me just explain. So here's my rectangular box. So they say here's my x0, y0, z0 here. So this is the x, that's the y down there, and the z is coming up here. So on the top face, the unit outward normal would be here, and that's pointing in the z direction, so the unit normal would just be k. And for the bottom face is down here, and the normal vector sticking out of the rectangular box would be like that, and that would be in the negative k direction, so that's why it's negative k. And then the right face would be here, so the unit normal vector sticking out of the right face would be here, and that's pointing in the positive y direction, so it's going to be j. And the left face would be over here, so the unit normal sticking out of the rectangle will be pointing this direction. That would be in the negative y direction, so it would be negative j. And then the front face would be here, so the unit normal vector sticking out of the front face would be this direction, and that's pointing in the x direction, so it would be I. And lastly, the back face would be back here, so the unit normal vector sticking out of that would be pointing in the negative x direction, so it'd be negative I. Okay, so let's keep going. Okay, so now we're going to verify the divergence theorem for this rectangular box. So we have all our faces here parameterized. So we're looking at the left side of divergence theorem. So we're looking at the surface integral. So it's going to be over the faces of our region. So the faces of our rectangular region would be these 6 faces. So we can break it into 6 integrals. Okay, so let's start doing these integrals then. So let me write it here. Let's do, say, S1 first. So let me write it here. Okay, so doing the surface integral over S1. So it's going to be surface integral over S1 equals then surface integral over S1 over your F, composed with S1, dot with the unit normal on your surface, outward normal for divergence theorem. So our outward normal for our surface we already established was K, and our vector field is up here. So I'm dotting with the K component, so it's just going to pick up the F3 guy. So you're just going to be evaluating your F3 at this point here. So let me write it down here. Okay, so doing the surface integral then, so dotting with K again, we'll pick up the F3, and here's my S1 down here. So I'm going to replace this in my F3, so it'll be xy z0 plus delta z. And if you go back and check, the x could range between, when you parameterize our S1, x0 and x0 plus delta x, they'll go on the limits on the integral. And y goes between y0 and y0 plus delta y, they'll go on the limits here. Okay, so this is my first surface integral over S1. Okay, so let's do S2 next. Okay. So let me erase a few things, we'll do S2. Okay, so let's go over S2 now. So the normal vector, the outward unit normal vector for the bottom face, or S2, we already established was negative K. So it's going to be then negative K here. It'll be F composed with S2 now. S2 is x, y, z0. So it's going to pick up the F3 again. But it's going to be dotted with negative K. So you'll have a minus sign in front of the F3 this time. It'll be x, y, z0, dx, dy. Oops. Should leave it up here. So when you dot with negative K, what your F here is going to pick up the F3. There'll be a minus sign in front this time. Then you're composing with S2, which is x, y, z0, so it'll go here. So that's my surface integral over S2 now. Okay, so let's summarize and we'll do S3 next. Okay. Okay, so now I've added my integral over S1 plus integral over S2 because they both had the same limits on them, so I can write them as a single integral. So the S1 had a positive sign in front of the F3, and it was like this, and the S2 guy had a minus sign in front of the F3. So therefore, adding these two S1 and S2 surface integrals, we'll get this guy. So I'm doing S3 next. So it's the right face. We said the unit normal is J. So it's going to be, should be S3 here. So it'll be F composite S3 dotted with outward normal. So the outward normal is J here. And again, my F vector field is this guy here, F1I, F2J, F3K. So dotting with J is going to pick up the F2 guy. So it's going to be F2 composite S3. S3 is X, Y0 plus delta Y, comma Z. So you're going to put that in place of X, Y, and Z in your F2 function, which I've done here. And the limits on the X, it should be Z here. Because S3 is XZ. So the limits on the X would be from X goes from X0 to X0 plus delta X, and Z goes from Z0 to Z0 plus delta Z here. Okay, let's keep going. Okay, so now we do the surface integral over S4. Well, S4 is the left face, and the unit outward normal vector we established was negative J. So here's my F over here again. So dotting with my F will pick up the F2 component, but it'll be a negative sign in front of the F2 this time. And my F4 is X, Y0, Z. So you're going to evaluate your F2 at this point here with a negative sign in front. And it's going to have the same limits as the S3 guy, which I have here. So they look similar. So I guess the same X and Y, X and Z limits, so we can combine these two integrals, like I did for the S1 and S2 guy up here. So let's combine those. So combining those, let me combine, erase a few things, combine those two. So doing that, we get then. Okay, so summarizing, so adding the S3 surface integral and the S4 one together, we can write a single integral. So it'd be F2x y0 plus delta y comma z and F minus F2 guy here. And then I'll let you check using the similar methods. If you do the surface integral over S5 and S6. So S5 you're dotting with i's, you're going to pick up the F1 component. You're going to evaluate at this point here, which I've done. And then for the S6 you're dotting with negative i's, you're picking up negative F1, evaluating at x0, y, z. So this would be all the surface integrals then. So let's summarize what we have. So summarizing, we've computed now the left-hand side of the divergence theorem for our example, the rectangular box. So it'll be the sum of the 6 faces. So we've shown it's equal to these three double integrals. So this is the left-hand side of divergence theorem for the rectangular box. So we denote say that here. Okay, so again, this is the left-hand side of the divergence theorem for our rectangular box. Okay, so this video is kind of getting long, so I'm going to end the video here. In the next video, we're going to show the right-hand side of the divergence theorem equals the left-hand side. So we're going to verify the divergence theorem for our rectangular box. Okay, so let's leave it there. We'll pick this up in part 2. Okay.